And now, in this lecture, we'll answer on two questions. In the first question, we'll find out the area of this semicircle that is inside quarter circle AOB. And in the second question, we'll find out the area of this green shape that is inside rectangle ABCD. So, we start with the first question. In the drawing, we have quarter circle AOB. We know that side AO equals to 5 units in its length. That is to say, the radius of this quarter circle AO equals to 5 units in its length. And inside this quarter circle AOB, we have this semicircle. And our mission is to find out the area of this semicircle. So, first of all, we will define the center of this semicircle. This point is point C. Likewise, we will define the first touching point of the quarter circle with the semicircle. This point is point F. We will define the second touching point of the quarter circle with the semicircle. This point is point G. We will define the point of tendency of tangent AO with this semicircle. This point is point H. And finally, we will define the point of tendency of tangent BO with this semicircle. This point is point L. In addition, we will define the radius of this semicircle as x. So, the radius CF of this semicircle is equal to x, according to our definition, and the radius CG of this semicircle also equals to x, according to our definition. In the next step, we join point C and L together by a straight line. CL is of course the radius of this semicircle that is equal to x according to our definition. We join points C and L together by a straight line. CH is also the radius of this semicircle that is equal to x. So here we can implement rule 1. Why? Because we have the radius CL of this semicircle, the radius CL that is equal to x is 1 to point L, that is the point of tendency of tangent BO with this semicircle. And whenever you have a radius that is 1 to the point of tendency, then tangent BO will be perpendicular to the radius LC. If BO is perpendicular to LC, it means that this angle equals to 90 degrees, and this angle is also equal to 90 degrees, according to rule 1. Likewise, we have the radius CH of this semicircle. The radius CH is 1 to point H, that is the point of tendency of tangent AO with this semicircle. And whenever you have a radius that is 1 to the point of tendency, then tangent AO will be perpendicular to the reduced edge C. If AO is perpendicular to edge C, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the sum rule on 1. So by doing these constructions, we created the quadrangle C edge OL. Inside this quadrangle C edge OL, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces angle. In total, it must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this 4 pieces angle must be equal to 90 degrees in its size. So inside quadrangle CHOL, we have 4 right angles. According to rule 5, any quadrangle that has 4 right angles must be this left angle equal to square. So we relate to quadrangle CHOL as a left angle because it has 4 right angles. But we also know that the opposite sides of a left angle are equal to each other. So left angle CHOL, side CH must be equal to the opposite side OL, but CH is x, therefore OL must be also equal to x. Likewise, according to the sum rule, in the sum of the angle CHOL, side CL must be equal to the opposite side OH, but CL is x, therefore OH must be also equal to x. So if we found out that quadrangle CHOL is not a rectangle but a square, why? Because of the fact that all of its sides are equal to each other. Each side of this square equals to x. So in the next step, we join points O and C together by side 9. By joining points O and C, we can do the right and associated triangle, triangle CLO. So in the next step, I'll copy the right and associated triangle, this right and associated triangle, triangle CLO in a new page, and we'll implement the Pythagoras theorem with this right and associated triangle, triangle CLO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the progression for Pythagoras theorem. So actually, this is the right and associated triangle, triangle CLO, that are copied from the original drawing. According to the Pythagoras theorem, in this right triangle CLO, CO squared, that is the square of the hypotenuse, must be equal to CL squared plus LO squared. So I write it down. CO squared, that is the square of the hypotenuse, equals to CL squared plus LO squared. The hypotenuse, the length of the hypotenuse CO is unknown, so we will leave it as it is. So CO squared equals to CL squared. CL is x, therefore CL squared is x squared plus LO squared. LO is also x, therefore LO squared is x squared. So in total, we found out that CO squared equals to x squared plus x squared. X squared plus x squared is 2x squared. So CO squared equals to 2x squared. Here we take out of this equation and finally get that CO equals to the square root of 2 times x units in its length. So CO equals to the square root of 2 times x units in its length. Here we have 97 CO equals to the square root of 2 times x units in its length. Point O is the center of the quarter circle. So from this point O, that is the center of this quarter circle, we have line segment OC that bisects chord FG. Again, line segment OC bisects chord FG. Why line segment OC bisects chord FG? Because of the fact that CF equals to x and CG also equals to x. So line segment OC bisects chord FG into two halves. Each half equals to x. CF equals to x and CG equals to x. And whenever we have a line segment that is drawn from the center of the circle or semicircle or quarter circle and bisect the line segment bisects a chord, then you can implement rule 7. So I'll repeat quickly on rule 7. According to rule 7, if a line segment that is drawn from the center of a circle bisects a chord, then the line segment is perpendicular to that chord. So in the drawing we have a circle, and this is point O, that is the center of the circle. So for point O, that is the center of the circle, we have line segment OM that bisects chord AB. That is to say, MA equals to MB. And whenever you have a line segment that is drawn from the center of the circle and it bisects a chord, like in this drawing, then line segment OM will be also perpendicular to AB. If OM is perpendicular to AB, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule 7. So repeat again, whenever you have a line segment that is drawn from the center of the circle and bisects the chord, then that line segment will be also perpendicular to that chord. So if we can implement rule 7 in our drawing. Because in our drawing, from the center of the quarter circle, that is to say from point O, we have line segment OC that bisects chord FG. So all the requirements of rule 7 are satisfied, and therefore we can implement here rule 7. According to rule 7, line segment OC will be also perpendicular to FG. If OC is perpendicular to FG, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 7. In the next step, we will join points O and F together by a straight line. Point O is the center of the quarter circle, point F is a point of the quarter circle itself. So this is exactly the definition of a radius. Therefore OF is the radius of this quarter circle, that is equal to 5 according to what is given as the question. So OF equals to 5. In the next step, I'll copy the right and green triangle, the right and green triangle CFO in the new page, and we'll implement the Pythagoras theorem on this right and green triangle CFO. Here by PT is a version for Pythagoras theorem. So actually, this is the right triangle CFO that I copied from the original drawing. Side CF equals to x, side CO equals to the square root of 2 times x units in this time, and FO, that is the hypotenuse of this right triangle CFO, FO equals to 5 units in its length. According to the Pythagoras theorem, in this right triangle CFO, FO square, that is the square of the hypotenuse, equals to FC square plus CO square. Again, FO square equals to FC square plus CO square. So I write it down. FO square, that is the square of the hypotenuse, equals to CF square plus CO square. FO, the hypotenuse FO is 5, therefore FO square is 5 square, that is 25, and 25 equals to CF square. CF is x, therefore CF square is x square plus CO square. CO is equal to 2 times x, therefore CO square is 2x square. So in total, I shall find out that 25 equals to x square plus 2x square. X square plus 2x square is 3x square. So 25 equals to 3x square. Here we divide this equation by 3 and finding here that x square equals to 25 over 3. Our mission is to find out the area of this semicircle. So what is the area of this semicircle? We know that the radius of this semicircle is x. If the radius of this semicircle is x, it means that the area of this semicircle must be equal to pi x square over 2. So I write it down. The area that we are looking for is the area of the semicircle. This equals to pi x square over 2. So it is pi over 2 times x square. And we just find out that x square equals to 25 over 3. So we can substitute x square in this equation by 25 over 3. We do it now. We get that the area of the semicircle equals to pi over 2 times x square. And x square is 25 over 3. So in total, the area of the semicircle equals to, here in the numerator we have 25 pi, in the denominator we have 2 times 3, that is 6. So in total, if we found out that the area of this semicircle, that is the area that we are looking for in this question, equals to either 25 over 6, 25 pi over 6 square units, or in terms of numbers, it is equal to 13.09 square units. Repeat again, if we found out the area of this semicircle equals to either 25 pi over 6 square units, or in terms of numbers, the area of this semicircle equals to 13.09 square units. So we finish with the first question. In the next step, I present to you the second question and answer on the second question. Our mission is in the second question is to find out the area of this ring shape. So in the drawing we have rectangle ABCD. We know that side AB of this rectangle ABCD equals to 5 units in its length. In addition, inside this rectangle ABCD we have this semicircle and this quarter circle. Quarter circle BPC. And our mission is to find out the area of this ring shape. So first of all, we will define the radius of this quarter circle BCP as x. So BC, that is the radius of this semicircle, equals to x according to our definition. We know that all the angles inside any rectangle are right angles, and therefore this angle ADC is equal to 90 degrees in its size. We will define the center of this semicircle, this point, as point O. We also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side BC must be equal to the opposite side AD. But BC is x, therefore AD must be also equal to x units in its length. AD is one side of rectangle ABCD, but AD is not only one side of rectangle ABCD, but it is also the diameter of this semicircle. So we know the diameter AD of this semicircle equals to x units in its length. If the diameter AD of this semicircle equals to x, it means that the radius must be equal to half of it. That is to say, the radius of this semicircle must be equal to x over 2 units in its length. So the radius OA of this semicircle equals to x over 2 units in its length. And the radius OD must be also equal to x over 2 units in its length. According to the sum rule that says that the opposite sides of a rectangle are equal to each other, so in rectangle ABCD, side AB must be equal to the opposite side DC. But AB is 5, therefore DC must be also equal to 5 units in its length. So I write it down. Side DC of this rectangle ABCD equals to 5 units in its length. So in the drawing, we have an external knot between this semicircle and this quarter circle PPC. That is to say, they touch each other externally at this point. We define their touching point, this point is point S. And whenever you have an external knot between two circles or semicircles or quarter circles, you can implement rule 10. So I'll click on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects the centers together passes through their touching point. So in the drawing, we have two circles, and they touch each other externally at this point, point P. That is to say, they have an external knot between them at this point, point P. The center of this circle is at point O. The center of this circle is at point M. And the straight line that connects the centers together is of course the straight line OM. And this straight line OM must pass through their touching point, that is point P. Again, the straight line OM must pass for point P, that is their touching point. Or OPM is one straight line. Again, OPM is one straight line according to this rule 10. So we can actually implement rule 10 in our drawing. Why? Because in our drawing, we have an external knot between this semicircle and this quarter circle. That is to say, they touch each other externally at this point, point S. Therefore, we can implement rule 10. The center of this semicircle is at point O. The center of this quarter circle PC is at point C. And the straight line that connects their centers together is of course the straight line OC. And according to rule 10, the straight line OC must pass through their touching point, that is point S. Again, the straight line OC must pass through point S, that is their touching point. Or OSP is one straight line. Again, OSP is one straight line according to rule 10. So we join points O and C together by straight line, and the straight line OC must pass through point S, that is their touching point. So it is very easy to see from the drawing that the straight line OC passes from point S, that is their touching point, exactly according to rule 10. So if the straight line OSC is one straight line, it means that OC equals to OS plus SC. Again, OC equals to OS plus SC. So I write it down. OC equals to OS plus SC. So OC equals to OS. OS is the radius of this semicircle that equals to x over 2 units in its length. So C equals to OS, that is x over 2, plus SC. SC is the radius of this quarter circle, that is equals to x according to our definition. So SC equals to x. So here OC equals to OS, that is x over 2, plus SC, that is x. So in total, OC equals to x over 2 plus x, that is either 1.5x or 3 over 2 times x units in its length. So if we found out that OC equals to 3 over 2 times x units in its length. So this is nice limit OC, that is equals to 3 over 2 times x units in its length. In the next step, I'll copy the right triangle ODC in the new page, and we'll implement the Pythagoras theorem on this right triangle ODC. Here by PT is the abbreviation for Pythagoras theorem. Actually, this is the right triangle ODC that I code from the original drawing. According to the Pythagoras theorem, in this right triangle ODC, OC squared, that is the square of the hypotenuse, equals to OD squared plus DC squared. So I write it now. OC squared, that is the square of the hypotenuse, equals to OD squared plus DC squared. The length of the hypotenuse OC is 3 over 2 times x, therefore, so OC equals to 3 over 2 times x, therefore OC squared will be equal to 9/4 times x squared. And it is equal to OD squared. OD is x over 2, therefore OD squared is x over 2 squared, that is x squared over 4. Plus DC squared. DC is 5, therefore DC squared is 5 squared, that is 25. So in total, if we found out that 9/4 x squared equals to 1/4 x squared plus 25. Here we subtract x squared over 4 from this equation, and we get that 9/4 x squared plus 1/4 x squared equals to 8/4 x squared. And here x squared over 4 minus x squared over 4 is 0, so we left only with 25 on the other side of the equation. So if we found out that 8/4 x squared equals to 25. 8 over 4 is 2, so this expression equals to 2x squared, and 2x squared equals to 25. Here we divide this equation by 2, and finally we get that x squared equals to 25 over 2. So here we'll take a root out of this equation, and finally we get that x equals to the square root of 25, that is 5, over square root of 2. So in total, if we found out that x squared equals to 25 over 2, and x equals to 5 over square root of 2 units in its length. Our mission is to find out the area of this green shape. So what is the area of this green shape? And from the drawing it is very easy to see that the area of this green shape equals to the area of rectangle ABCD minus the area of this semicircle minus the area of this quarter circle. Repeat again, the area of this green shape equals to the area of rectangle ABCD minus the area of this semicircle minus the area of this quarter circle. So I'll write it down. The area of the green shape equals to the area of rectangle ABCD minus the area of the semicircle minus the area of the quarter circle. So what is the area of rectangle ABCD? We know that the area of any rectangle equals to the length of the rectangle times the width. The length AB of rectangle ABCD equals to 5 units in its length. The width BC equals to x. So in total, the area of rectangle ABCD equals to 5x. Minus the area of this semicircle. The area of any semicircle equals to pi times the radius of the semicircle squared divided by 2. And therefore, the area of this semicircle, you know that the radius of this semicircle is x over 2. Therefore, the area of this semicircle must be equal to pi times x over 2 squared divided by 2. So I write it down. The area of the semicircle in total equals to pi times x over 2 squared divided by 2. Minus the area of this quarter circle. The radius of this quarter circle is x. Therefore, the area of this quarter circle must be equal to pi x squared over 2. So I write it down. The area of the quarter circle equals to pi x squared over 4. Again, the area of this quarter circle equals to pi x squared over 4. So the area of the green shape equals to 5x. And here we have minus pi over 2 times x over 2 squared. X over 2 squared is x squared over 4. So in total, the value of this expression is equals to pi x squared over 2 times 4. And then also minus pi x squared over 4. So the area of the green shape equals to 5x, and here we have minus pi x squared over 2 times 4 is 8. So in total this expression equals to minus pi x squared over 8. And here we have minus pi x squared over 4. Here we multiply both the numerator and the denominator of this expression by 2, and we get that this expression will be equal to minus 2 pi x squared over 8. So the area of the green shape equals to 5x, and here we have minus pi x squared over 8 minus 2 pi x squared over 8 equals to minus 3 pi x squared over 8. So if we found out the area of the green shape equals to 5x minus 3 pi x squared over 8. But we already found out that x equals to 5 over square root of 2 and x squared equals to 25 over 2. Therefore, we can substitute x in this equation, in this expression by 5 over square root of 2, and we substitute x squared in this expression by 25 over 2. We do it now and we get that the area of the green shape in total equals to 5x, and x equals to 5 over square root of 2, and here we have minus 3 pi over 8 times x squared. X squared equals to 25 over 2. So if we found out that the area of the green shape equals to 5 times 5 is 25, so in total this expression equals to 25 over square root of 2. Minus, here in the numerator of this expression we have minus 3 pi over 25, that is minus 75 pi over 8 times 2 is 16. So in total, this expression equals to minus 75 pi over 16. And the area of the green shape in total equals to 25 over square root of 2 minus 75 pi over 16 square units. And the value of this expression in total is equals to 2.95 square units. So if we found out the area of this green shape equals to 2.95 square units. We finish with the second question. In the next step, I'll summarize the lecture. We'll start with the first question, of course. In the first question, our mission was to find out the area of this semicircle that is located inside quarter circle AOB. So in the domain we have quarter circle AOB. We know that the radius of this quarter circle AO equals to 5 units in its length. So inside this quarter circle AOB we have this semicircle, and our mission is to find out the area of this semicircle. First of all, we define the center of this semicircle. This point is point C. We define the first touching point of the semicircle, the quarter circle. This point is point F, and we define the second touching point of the semicircle, the quarter circle. This point is point G. Likewise, we define the point of tendency of tangent BO with this semicircle. This point is point L. And finally, we define the point of tendency of tangent AO with this semicircle. This point is point O. It's point H. In addition, we define the radius of this semicircle as x. Therefore, the radius CF of this semicircle equals to x, and the radius CG of this semicircle also equals to x. In the next step, we join points C and L together by a straight line. CL is of course the radius of this semicircle, that is equals to x. Likewise, we join point C and H together by a straight line. CH is also the radius of this semicircle, that is equals to x, according to our definition. So here we can implement rule 1. Why? Because we have the radius CL of this semicircle, the radius CL that is equals to x. The radius CL is drawn to point L, that is the point of tendency of tangent BO with this semicircle. And whenever your radius that is drawn to the point of tendency, then tangent BO will be perpendicular to the radius LC. If BO is perpendicular to LC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. Likewise, we have the radius CH of this semicircle, the radius CH that is equals to x. The radius CH is drawn to point H, that is the point of tendency of tangent AO with this semicircle. Whenever your radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius HC. If AO is perpendicular to HC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to the same rule, rule 1. So by doing these constructions, we can generate quadrigonal CHOL. Inside quadrigonal CHOL, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth again. In total, they must be equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrigonal is equal to 360 degrees. And therefore, this fourth angle must be equal to 90 degrees in its size. So inside quadrigonal CHOL, we have 4 right angles. And according to rule 5, any quadrigonal that has 4 right angles must be a rectangle, if not a square. So we relate to quadrigonal CHOL as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So an rectangle CHOL, side CH must be equal to the opposite side OL. But CH is X, therefore OL must be also equal to X. Likewise, according to the same rule, in the same rectangle CHOL, side CL must be equal to the opposite side OH. But CL is X, therefore OH must be also equal to X. So what we found out, that quadrangle CHOL is not a rectangle but a square. Why? Because of the fact that all of its sides are equal to each other. Each side of this square equals to X. In the next step, we join points O and C together by straight line. By joining points O and C, you can then write an associated triangle, triangle CLO. So, in the next step, I copied the right and associated triangle, triangle CLO in a new page, and implemented the Pythagoras theorem in this right and associated triangle, triangle CLO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Simply, this is the right and associated triangle, triangle CLO, that I got it from the original drawing. According to the Pythagoras theorem, in this right and associated triangle, triangle CLO, CO squared, that is the square of the hypotenuse, equals to CL squared plus LO squared. Again, CO squared equals to CL squared plus LO squared. The length of the hypotenuse CO is unknown, so we leave it as it is. So CO squared equals to CL squared. CL is X, therefore CL squared is X squared, plus LO squared. LO is also X, therefore LO squared is X squared. So in total, we should find out that CO squared equals to X squared plus X squared. X squared plus X squared, X squared plus X squared is 2X squared. So we should find out that CO squared equals to 2X squared. Here we took a root out of this equation and finally found out that the length of the hypotenuse CO is equals to the square root of 2 times X units in its length. Here we should find out that this line segment CO is equals to the square root of 2 times X units in its length. Point O is the center of this quarter circle. So from point O, that is the center of this quarter circle AOB, we have line segment OC that bisects chord FG. Why line segment OC bisects chord FG? Because of the fact that CF equals to CG equals to X. So line segment OC bisects chord FG into two halves. Each half equals to X. CF equals to X and CG equals to X. So whenever you have a line segment that is drawn from the center of the circle or semicircle and quarter circle and it bisects the chord, like in this drawing, we have line segment OC that bisects chord FG, you can implement rule 7. So I'm just clicking on rule 7. According to rule 7, if a line segment that is drawn from the center of the circle bisects the chord, then the line segment is also perpendicular to that chord. So in the drawing we have a circle, and this is point O, that is the center of the circle. So from point O, that is the center of the circle, we have line segment OM that bisects chord AB. That is to say, MA equals to MB. Again, whenever we have a line segment that is drawn from the center of the circle and bisects the chord, like in this drawing, you can implement rule 7. So according to this rule 7, line segment OM will be also perpendicular to chord AB. Again, line segment OM will be also perpendicular to chord AB. If OM is perpendicular to AB, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule 7. So we can actually implement rule 7 in our drawing. Why? Because in our drawing, we know that point O is the center of the quarter circle. So from the center of the quarter circle, that is point O, we have line segment OC that bisects chord FG. So all the requirements of rule 7 are satisfied, and therefore we can implement rule 7. According to rule 7, line segment OC will be also perpendicular to chord FG. Again, according to rule 7, line segment OC will be also perpendicular to chord FG. If OC is perpendicular to FG, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 7. So in the next step, actually join points O and F together by a straight line. Point O is the center of the quarter circle, point F is the point on the quarter circle itself. So this is exactly the definition of a radius. Therefore, OF is the radius of this quarter circle, that is equals to 5, according to what is given as the question. So in the next step, I copy this right angle triangle CFO in a new page, and we implemented the Pythagoras theorem on this right angle triangle CFO. So actually, this is the right angle triangle CFO that I copied from the original drawing. Side CF equals to x units in its length, side CO equals to the square root of 2 times x units in its length, and finally the hypotenuse FO equals to 5 units in its length. According to the Pythagoras theorem, in this right triangle CFO, FO squared, that is the square of the hypotenuse, equals to FC squared plus CO squared. Again, FO squared equals to CF squared plus CO squared. FO is 5, therefore FO squared is 5 squared, that is 25. And it is equals to CF squared. CF is x, therefore CF squared is x squared plus CO squared. CO is equal to 2 times x, therefore CO squared is 2x squared. So in total, we should find out the 25 equals to x squared plus 2x squared. X squared plus 2x squared is 3x squared. So we should find out in total the 25 equals to 3x squared. Here we divided the equation by 3, and finally found out that x squared equals to 25 over 3. Again, x squared equals to 25 over 3. Our mission is to find out the area of this semicircle. What is the area of this semicircle? Actually, the area of any semicircle equals to pi times the radius of the semicircle squared. The radius of this semicircle is x, therefore the area of this semicircle must be equal to pi x squared over 2. Again, the radius that you are looking for, the radius of the semicircle is equal to pi x squared over 2. So it is pi over 2 times x squared. And just right now found out that x squared equals to 25 over 3. Therefore, we can substitute x squared in this equation by 25 over 3. We get it, okay. And actually found out that the area of the semicircle equals to pi over 2 times x squared. X squared is 25 over 3. So in total, we found out that the area of the semicircle equals to, here in the numerator of this expression we have 25 pi over 2 times 3, and 2 times 3 is 6. So in total, the area of the semicircle equals to either 25 pi over 6 square units, or in terms of numbers, the area of this semicircle equals to 13.09 square units. We finish with the first question. In the next step, I shall present to you the second question and we solved it. Our mission in the second question is to find out the area of this green shape. So in the drawing we have rectangle ABCD. We know that side AB of this rectangle ABCD equals to 5 units in its length. In addition, inside this rectangle ABCD we have this semicircle and this quarter circle BCP. And our mission is to find out the area of this green shape. So first of all, we define the radius of this quarter circle BPC as x. So the radius BC of this quarter circle BPC equals to x according to our definition. We know that all the angles inside the rectangle are right angles. So this is angle ADC inside rectangle ABCD that equals to 90 degrees in its size. We also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC, but AB is 5, therefore DC must be also equal to 5 units in its length. Likewise, according to the same rule, in the same rectangle ABCD, side BC must be equal to the opposite side AD, but BC is x, therefore AD must be also equal to x units in its length. We define the center of this semicircle, this point is point O. We know that AD equals to x. AD is one side of rectangle ABCD, and AD is also the diameter of this semicircle. So we know that the diameter of this semicircle AD equals to x. If the diameter of this semicircle is x, the radius must be equal to half of it. So the radius must be equal to x over 2. So we know that the radius of the semicircle is x over 2. So the radius OA of this semicircle equals to x over 2 units in its length, and the radius OD of this semicircle also equals to x over 2 units in its length. Okay. So here we have an external launch between this semicircle and this quarter circle. That is to say, they touch each other externally at this point. We define their touching point, this point is point S. And whenever you have an external launch between two circles, semicircles or quarter circles, we can implement rule 10. So I'll repeat with you on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes for their touching points. So in the drawing, we have two circles and they touch each other externally at this point, point P. That is to say, they have an external launch between them at point P. The center of this circle is here at point O. The center of this circle is here at point M, and the straight line that connects the centers together is of course the straight line OM. And this straight line OM must pass for their touching point, that is point P. Again, the straight line OM must pass for point P, that is their touching point. Or OPM is one straight line. Again, OPM is one straight line according to this rule, rule 10. So I can actually implement rule 10 in our drawing. Why? Because in our drawing we have an external launch between this semicircle and this quarter circle. That is to say, they touch each other externally at this point, point S. Therefore, I can implement rule 10. The center of this semicircle is here at point O. The center of this quarter circle is here at point C. And the straight line that connects the centers together is of course the straight line OC. And this straight line OC, according to rule 10, must pass for their touching point, that is point S. Again, the straight line OC must pass for point S, that is their touching point. Or OSC is one straight line. Again, OSC is one straight line according to rule 10. If OSC is one straight line, it means that OC equals to OS plus SC. Again, OC equals to OS plus SC according to rule 10. So OC equals to OS. OS is the radius of this semicircle that is equals to x over 2. And SC is the radius of this quarter circle that is equals to x. So in total, we found out that OC equals to x over 2 plus x, that is 1.5x, or it is either 1.5x or 3 over 2 times x units in length. So we found out that the opposite OC of this right triangle ODC is equals to 3 over 2 times x units in its length. In the next step, I copied this right triangle ODC in a new page and we implemented the Pythagoras theorem on this right triangle ODC. So actually, this is the right triangle ODC that I copied from the original drawing. We now found out that OC equals to 3 over 2 times x units in its length, OD equals to x over 2, and DC equals to 5. According to the Pythagoras theorem, in this right triangle ODC, OC squared, that is the square of the hypotenuse, must be equal to OD squared plus DC squared. Again, OC squared equals to OD squared plus DC squared. OC is 3 over 2 times x, therefore OC squared is 9 quarters x squared. Plus OD squared, OD is x over 2, therefore OD squared is x squared over 4, plus DC squared. DC is 5, therefore DC squared is 5 squared, that is 25. So in total, we found out that 9 quarters x squared equals to 1 quarter x squared plus 25. Here we subtract x squared over 4 from this equation, we finally found out that 9 quarters x squared minus 1 quarter x squared equals to 8 quarters x squared. Here, x squared over 4 minus x squared over 4 is 0, so we left only with 25 on the other side of the equation. So in total, we found out that 8 quarters x squared equals to 25. 8 over 4 is 2, so this expression is in total equals to 2x squared, 2x squared equals to 25. Here we divided this equation by 2, and finally found out that x squared equals to 25 over 2. Here we took root out of this equation, and finally found out that x equals to the square root of 25, that is 5, over square root of 2. Again, x equals to 5 over square root of 2 units in its length, and x squared equals to 25 over 2. Our mission is to find out the area of this green shape. So what is the area of the green shape? For the drawing, it is very easy to see. The area of this green shape equals to the area of rectangle ABCD minus the area of this semicircle minus the area of this quarter circle. Again, the area of this green shape equals to the area of rectangle ABCD minus the area of this semicircle minus the area of this quarter circle. Repeat again. The area of the green shape in total equals to the area of rectangle ABCD minus the area of the semicircle minus the area of the quarter circle. So what is the area of rectangle ABCD? Note that the area of any rectangle equals to the length of the rectangle times the width. The length AB is 5, the width BC is x. So total the area of rectangle ABCD equals to 5x. And again, the area of rectangle ABCD equals to 5x. Minus the area of this semicircle. What is the area of this semicircle? The area of this semicircle equals to pi times the radius of this semicircle squared divided by 2. The radius of this semicircle is x over 2, therefore in total the area of this semicircle must be equal to pi times x over 2 squared divided by 2. Repeat again, the area of this semicircle In total it is equals to pi times x over 2 squared divided by 2. Minus the area of this quarter circle. What is the area of this quarter circle? We know that the radius of this quarter circle is x. Therefore the area of this quarter circle must be equal to pi x squared over 4. And again the area of the quarter circle equals to pi x squared over 4. So the area of the ring shape in total equals to 5x. Here we have x over 2 squared. X over 2 squared is x squared over 4. So in total this expression equals to pi over 2 times x squared over 4. Pi over 2 times x squared over 4. Minus pi x squared over 4. So the area of the green shape in total equals to 5x. And here we have pi x squared over 2 times 4, that is 8. So in total this expression equals to minus pi x squared over 8. And here we have minus pi x squared over 4. Here we multiply both the numerator and the denominator of this expression by 2. And we found out that this expression equals to minus 2 pi x squared over 8. So the area of the green shape equals to 5x. And minus pi x squared over 8 minus 2 pi x squared over 8 equals to minus 3 pi x squared over 8. So in total, we found out that the area of the green shape equals to 5x minus 3 pi over 8 times x squared. But we already found out that x equals to 5 over square root of 2 and x squared equals to 25 over 2. Therefore we can substitute x in this expression by 5 over square root of 2, and we can substitute x squared in this expression by 25 over 2. We did it, and we actually found out that the area of the green shape in total equals to 5x, and x is equals to 5 over square root of 2 minus 3 pi over 8 times x squared, and x squared is 25 over 2. So in total the area of the green shape equals to 5 times 5 is 25. So in total this expression equals to 25 over square root of 2. And here we have in the numerator in this expression we have minus 3 pi over 25, that is minus 75 pi over 8 times 2 is 16. So in total the value of this expression is equals to 75 pi minus 75 pi over 16. And the area of the green shape in total equals to 25 over square root of 2 minus 75 pi over 16 square units. In terms of numbers, the area of this green shape equals to 2.95 square units. Okay, again, the area of this green shape equals to 2.95 square units. Okay, thank you very much.